Hello, everybody. I'm going to slowly start, hoping that everybody who wanted to join joined or join brief soon. My name is Gosia Konwerska. I work as a kernel developer for Wolfram Research, and I'm going to be talking about spatial statistics, looking from the data side mostly, but also I'll talk a bit about the models. And when we talk about the spatial point data, here we are concerned about point patterns, so say events in space. So this is like the trees in the forest, gold deposits, and this is the situation where interpolation between points doesn't make sense. So this is not, or maybe some people are familiar, kriging. We are in a point pattern situation. Okay, so to start with, we introduced the new data container, which is called spatial point data. And this is a container for points, locations, and observation region. And there are three main ways to obtain spatial point data. We can create it directly from points, or from points in region, or from points with annotations, and that can have region or not region. We can generate spatial point data from a point process, and we can also obtain spatial point data from a curated collection of resource objects. So first I want to show how to create a spatial point data from your own data, let's say. So say that we fetch some data and some largest cities in Canada, and you see they come to us as entities, and we can input them as locations directly into the spatial point data, and we can provide the region, which is also an entity. And then we have a spatial point data, so we call the elided form, which tells us here in this, here the data type is geographical. We have 96 points. The physical dimension is 2. And if you expand it, you get a little more information about the region. We can then just plot the points using the geolist plot. And we can extract more information from the spatial point data via properties. The quick information about the data, it's under the summary, which kind of gives us the similar information that the elided form, but also tells us about the annotations, and we see that there are no annotations. And we can extract observation region and look at the points. And this is a geographical data, so the points are stored in a compact way in a single geoposition. So as I mentioned, there are no annotations, so we got the empty association here, but we can add information about the points. So say that I'm gonna extract the names for all the cities, and then I'm gonna create a new object that has the locations, but also has the information about the names for each city. So that's our annotation. And the way that it's here, it's given with a key, which is the name of the keys, the names. And we give the same region. So now when we look at the summary, it will have the line here about the annotations, and it will give us the keys for the annotations. And then we can use these annotations in a visualization, for example, create a tooltip, and then plot everything using geographics, where we can show the whole region, the locations, and when you move around, you can just basically see the names of all the locations. Okay, a side note, I mentioned that we can put in observation region, and so it's important to know that not every region can be a valid observation region. It has to be parameter free, full dimensional, and bounded. And we introduced the function that tests these conditions. This is spatial observation region Q. And so when we look at the region that I used before, the entity country Canada, and we can test it that it's true because this entity has a polygon property. And if the region is not provided, then it's going to be inferred from the points using the Ripley-Rason estimator, which you can think as a dilated convex hull. And so here I create a spatial point data just with the cities, and I can extract observation region, which is a polygon based on the geopositions. And you can visualize this region with the points. And so now you see that this region is a polygon in space, and it's not the whole Canada country as we had before. And the way to obtain the Ripley-Rason region is also a function in Wolfram Language now. So you can generate some random points, say, on a disk, and create the Ripley-Rason region on the points. And then when we visualize this, we see that The blue is the original region from which we generated the points. We see the points and we see the orange, the Ripley raison region. The idea about, with the Ripley raison region is that no points will be close to the boundary. So the dilation happens to kind of create the region which will not have the observation points close to the boundary. And when you look at the original region and the points, you see that some points are almost sitting on the boundary, just like here. Okay, so we can obtain spatial point data simulating a point process, and the function to simulate from point processes is called a random point configuration. And the process from which I will simulate here, it's in homogeneous Poisson point process, where we can specify the density as a function of location, and we provide the dimension. And I will not talk much about the models, the point processes. That's going to be covered more in Eduardo's talk at 11:30, so right after this one. So let's define the process and let's sample from the process over the disk. So you see that the random point configuration takes the process and takes the region. And now we see that the data type is Cartesian. We have 2,618 points and the physical dimension is 2. And then we can visualize the plots with the region. Okay, and then we can also get the spatial point data from, set of curated spatial point data sets that will be available as a resource objects. And for now, what I do is I load this locally from my computer here, but that will be made public at some point. And so here I have a resource object, and to extract the data, the spatial point data, we have to use the resource data that gets us the main data, which is the form in the form of a spatial point data. And when we study the data, summary is a good place to start, besides, plotting. So I can plot and look at the summary, and it tells me that I have annotation here. So I want to see what's the annotation, and it gives me that the set of names for the species. So I can see that I have 2 types of species. We have a way to create a subset from the original data, which is called spatial point select. So in a spatial point select, I give the original data, and then I would like to select all the points or the locations that the species is the cataglyphis. So that gives me another spatial point data, and I do the same for the second type of species. And your sanity check is that you only keep the right species. So the annotations on my subset only have 1 type of species. And then we can plot them both colored differently and see how they intermingle or whether they not intermingle. Okay. In study of data, we also want to understand, how the point density varies, per length or per area or per volume, depending on which dimension you are working. And so point density, it's generally a function that describes this variation. And this is not maybe a density in a strict sense, because when we integrate this function over the observation region, we're gonna get the total number of points within this observation region. And in Wolfram Language, we have 3 functions that are dedicated to compute point density. They all use different distinct approaches. So we have point density, histogram point density, and smooth point density. And I will talk about each in a bit more detail. Point density is an adaptive density estimator. It's 1 point per bean. So let's recall our ant data. And we can compute the point density using Voronoi tessellations. And we can show the density with the data points. So you see one point per bean, and the closer the points are to each other, the smaller the beans get, and so we have a higher value of density. What you see also here is that point density returns point density function, and this is going to be the output for all the density functions. And point density function is a function of a location, so we can plot it as, using plot3D, we can plot the surface for the points, the locations inside the observation region. Histogram point density is a partition-based estimator, and the bean specification will control the smoothing. So automatically, this is what we get when we want to compute histogram point density on data. It's a binning, which is aggregated mesh method. And to show it better with the points, we see that the beans have their own color, and we can specify the shape of the beans. So maybe I want to have a hexagon, and also we can specify the size, which can be controlled, for example, by the number of beans that we want. And so this is the plot for a different bean count. So you see, the more beans we have, the more varied the density function is. Less beans gives us a more smooth result. Now, smooth point density is a kernel-based estimator, which is controlled by the bandwidth and the kernel functions. And this is extension of the kernel mixture distribution and smooth kernel distribution to regions. So we again obtain the point density functions. In the properties of this type point density functions, we see distribution, and this distribution corresponds to either kernel mixture of smooth kernel distribution, and the choice of which can be controlled via options in smooth point density. And so we can, for example, plot PDF of this distribution, because this is well-defined distribution in Wolfram language. Okay, the next question that we ask in studying point data is whether the points in the collection are uniformly distributed and independently from each other. So whether they are having interactions like repelling each other or attracting each other. So if a data is independently and uniformly distributed, the points, then we call it exhibiting a complete spatial randomness. And it also means that the point density is constant across the observation region, and the numbers of points in any subregion are an independent and identically distributed random variables. And the model for this is a Poisson point process, where the first parameter here is exactly this constant point density, and the second parameter is the dimension in the space. So when you sample from this point process, you can look at the points and you kind of see, well, I don't know if this is uniform or not. And so we know that the point density should be constant, so we can visualize the point density of the sample and see if this is constant. And I still cannot really tell, because the density visualization does not give us a computable answer, and therefore we need a test. We need to be able to have a hypothesis test, and we introduce spatial randomness test, which works as any other test in Wolfram language. So by default, if you just input the sample, it returns the p-value, but we can also ask for the test conclusion. And here we see that this is not passing the test, actually, this data, even though it was generated for the Poisson point process. And also notice that it's based on a specific test, in this case, chi-square test. And so spatial randomness test is really a super test, and we have more tests available inside, and you can use another test, for example. And here the p-value, it's on the borderline. So it really varies, as always. Okay, and that was kind of show you that it's difficult to tell whether the data it's truly random, spatially random. And this is another example that shows why things are kind of difficult to tell. And so I have an example here for cluster data, and I will simulate two cluster processes over a geographical region, and they will differ only in the average number of points per cluster. The first parameter here is the intensity of points in the parent process, so the cluster centers, and cluster radius tells you the size of the cluster. So the first process and the second process is called Mattern point process, and I just simulate both processes. And this might take a little bit, but don't be discouraged. Okay, so we have two samples. So then we can just plot them next to each other. Okay, and so they look they look different because the second sample has more points. And now we can test, the spatial randomness. And so here we have that they're not rejected. And the funny thing is that I was doing this, on with a different seed, one was rejected, one was not rejected. But basically the point is that in this situation, the test does not reject the null hypothesis. So even though both both samples are created using the cluster model, the test tells us that they will may come from uniform, uniform process, so they may be uniformly distributed. So this is not easy in a way. This is not evident to identify your, the model from which your data comes. Okay, and to further study this this question, of complete spatial randomness, we have the second order measures, which are called homogeneity measures, and they also study how, how the points, how uniform the points are distributed in the observation window. And so they are the functions here, and I group them because they have connections. So it's replicate and Besagel. Besagel is basically a function of replicate. Empty space F, nearest neighbor G, spatial J, where spatial J is a function of the first two, and we have a per correlation G. So when we look at the replicate at some distance r and multiply this by the mean point intensity, it gives us the expected number of points within the distance r. And as I said, Besagel is just a function of replicate. And usually these two statistics are used to compare the data with the ideal model of the Poisson point process, for which the replicate is just some polynomial of order of the dimension, and Besagel it's going to be always linear in R. So again, I'm going to take the cluster process and then just compare the replicate of this cluster sample with the ideal replicate of the Poisson point process. And one thing to notice here is that we get the point statistic function. Before, for the densities, we get the point density function. Here we get a point statistic function. And so we can plot and compare the cluster sample and the Poisson process, and see that they are different. And here for the point statistic functions, we have the properties stored. And I want to just mention this one, the boundary correction. This is a method which is used to account for the points being on the boundary or very close to it. And we can extract the boundary correction that was used in this case to compute this replicate, the Borden margin. And this can be changed to different methods, or can be disabled completely using option spatial boundary correction. So empty space F and nearest neighbor G are almost the same because they give probability of finding a point within distance R. It only different from where. And so either from arbitrary location, as in empty space F, or from a typical point in the collection. And spatial J is the function of the first two. And so when you look at the Poisson point process, both the probability of finding a point within distance R from a location or from a typical point in the data are exactly the same. And hence the spatial J for the Poisson point process is equal 1. And so what we can do here is, for example, compare the two for a data. This is a forest data which has observation region, which is the rectangle of size 1. And this is a region scaled, and 1 corresponds to 924 feet. So you can plot the data, and you would like to know some information, about the data to have some conclusions, what happens. So what I do here, I plot nearest neighbor G, and I scale it to the feet, so it will it will give you the probability of finding a tree within radius r feet from either another tree or a random location within the observation region. And as you see, this point statistics here, right, it's computed without any radius. And so this is a pre-computed function. And then when I want to plot it here, you know, the computation for each radius has to happen. And hence it takes a little bit of time to get the plot. And so what we see here is that probability from a location is, is lower for a small radiuses. So it's more likely to find another tree from if you are a tree. So that may hint that basically we're looking at the cluster data. Not definitive answer. It's one of the hints that we get studying data. And per correlation G, also called radial distribution function. This is proportional to the probability density of finding 2 points at a given distance apart. And that could be understood as a derivative of nearest neighbor G, which was, you know, having a point, you know, finding the probability of nearest neighbor G was giving you probability of finding a nearest neighbor, or, you know, a point within a given distance from established point in the data. And despite the name, per correlation G is not a correlation in the usual sense, with values varying between -1 and 1. And the range is from 0 to infinity, and 1 is the value corresponding to complete spatial randomness. So this is as expected. The per correlation G on a Poisson point process, it's always 1. It's independent on any you know, parameter here, so point density, dimension, no radius. And we can use per correlation DTU to see if there is a hardcore radius in the per collection. So whether there is some repelling force in the data. And you can see that probability of finding 2 points, which are, you know, small distance apart, is 0, which would indicate that there is indeed a hardcore radius. And that agrees with our model, which is exactly, you know, as called here. This is the mean point density, and this number here is the hardcore radius, which means we can't find any 2 points closer to each other than this number. Okay, and then last but not least, there is another object that we introduce. It's called spatial binned point data, and it's an object that it's designed to store aggregated spatial point data in a neat and nice way, because a lot of times the point data will come to us in the aggregated form. So you know, the aggregation happens per zip area, per county, per state. And what I want to show here is that the data comes, you know, in, you know, this kind of way. So they say we have the COVID historical test results from the Illinois Department of Public Health website. This is a JSON file. And, you know, like what we're trying to do is to get the information about the latest, you know, update, to get the total numbers of, you know, confirmed cases per county in Illinois. So you can see that we can get the date of the last update. Then if I just ask, you know, what is, you know, where's my data, you know, this looks like that. So, okay, so I'm getting closer, but in a way, this is all manipulation on, you know, which parts I need to take. And so to extract the counties, you know, I need to take this part here. And the next step is to look at this and see what has to be done to make sure that we can then match these counties with the entities in Wolfram language that will give us the proper locations that is understood. And the first thing that jumps, you know, out is this, that the width, for example, has a space, and in Wolfram language the entities are written without spaces. The other issue is that we have out of state, and we also have unassigned, so we need to drop them. So I'm gonna find the positions for these two problematic, you know, states that we need to drop, and then I'm gonna create the bins. And, you know, one more thing is that Chicago in the entity framework is not a county, it's a city, so we need to input this as an entity city. Everything else goes as administrative division, so we create the bins. We're gonna check that we actually have what we want, so we get the entities. Now from the values, we need to drop the positions that correspond to unassigned and out of state. Sanity check, are our lengths the same? Okay, between the values and the bins. And then the nice part is that we create the special bin point data, bins and values. and it's running. And I'm just checking if everything is. Let's try again. Okay, while this is running, we can look at the plot. Maybe not. I'm just gonna abort that and show you the plot. So basically what we will get eventually is the ability of geo-region value plot to support directly the spatial bean point data. And I'm just gonna go and reevaluate stuff and see that we get everything. So I evaluated this and everything looked good. So, well, bad things happen to good people for no reason. But anyway, I will let it run and see. And in the meantime, that's the end of the talk. And I thank you. And I'm gonna see if there are any questions that I can answer. But I'm just gonna keep looking at this. This is boring. Okay. So I'm gonna start from the talk. As the okay. Okay, I don't see any. I see some. Yes.
Can you hear me?
Yes. What's your question?
So I was wondering, it was an awesome talk.
Thank
I was
you.
wondering if these functions take like a periodicity metric, like such that, say, if you're running a molecular dynamics simulation, you typically will use a unit cell where if you go through the right side of the unit cell, it will come back through the left, such that there's a periodicity element to it, and distances can be like different because of that. Say, if you're near the left side of the wall and the right side of the wall, the periodic distance is smaller than the actual distance. Do these take an argument that accounts for that?
I don't know. You know, we created this in a way that it's somewhat general, you know, container, and it can take a lot of data. It can take the structured data on a regular grid as well. It's just that it's not designed to, you know, to look into the interpolation between the points. So I mean, you know, feel free to, you know, if you have the example, we can, you know, meet up later, or you can shoot me an email you know, with this, and then just try it if it works. So because I don't think I've come across the type of data that you're talking about. So that's as far as I can tell. Sorry.
Great, thank you.
We have a couple of questions in the Pathable chat.
Well, sorry, the thing is just refreshing on me. Can the points be geopositions? Yes, and they are. That's what I was showing at the beginning. The Canada data, the cities are geopositions. And yes, the methods compensate for the non-Cartesian coordinates. In some cases, we look at the geodistance, and you know, and we look at you know, we lose the geodistance. The problem is that the computations are much slower. So in what we are doing in many of these computations here in the densities or in the homogeneity measures is that we project and then do the computations and then go back to the geospace. Okay. Oh, the good thing is that you can see now the output of the spatial bean point data. That will tell you that it's a geographical data. We have 103 beans, and it tells you that the type of beans was given as a list. So, okay, I'm still looking if there are any more questions, and The notebook, yes, I think I will have to make a little changes to the notebook before I upload it and make it available. Also, you know, this is all very experimental functionality, and so just want to make sure that there is a, you know, a beta coming that this functionality works, you know, and that we have things kind of finalized. So yes, and okay. So I guess that's all for the questions I see, and since we are out of time, I'm gonna just say thank you. And as I said, if some questions pop up later, you know, feel free to contact me and stop by Eduardo's talk, which starts right now. So thank you.
Thank you all for coming.